So today we're diving into something that's maybe the most important and least talked about part of quantum computing. It's this invisible shield that's the entire field absolutely cannot live without. And it's not about building more qubits, it's about a much deeper problem. How do you protect the ones you already have? Let's get into it because here's the thing, the fundamental challenge, the big inconvenient truth of a quantum world is not a bug in the code or a problem with the hardware. The biggest threat to a working computer is the universe, reality itself. To put it as simple as possible, qubits, the very heart of these machines, are just unbelievably fragile. I mean, they exist in the super delicate quantum state, and the slightest whisper from the outside world can just poof, erase everything that they're holding. And what does it take to destroy that state? Almost anything. A tiny bit of heat, a stray magnetic field from the wiring in the walls, or even the computational gates themselves not being absolutely perfect. Heck, the very act of trying to look at a qubit can be enough to knock it off course. This constant, relentless barrage is what scientists call quantum noise. So here's the game plan for this video. We're going to really understand this threat. Then we'll look at a simple trick from the computers we use every day. After that, we'll see the wild quantum leap that makes fixing these errors even possible. Then we'll finally get into the actual rulebook scientists use. And finally, we'll see how they're using it to build the ultimate quantum fortress. So this fragility, it isn't just some minor annoyance, it's a central problem. Trying to run a long calculation on a quantum computer right now is kind of like trying to whisper a really complicated secret across a loud, crowded party. By the time it gets to the other person, you can almost be certain that the message is going to be completely garbled. So how on earth do we fix this? Well, let's start with the solution we all know. How do you make sure your message gets through in that noisy room? You just say it again and again. You repeat it. In classical computing, the fix is beautifully simple. Just add redundancy. If you want to protect a single bit, let's say 0, you don't just send it once. You send it 3 times. 0, 0, 0. If some noise flips one of those bits along the way, you might get 0, 1, 0. No problem. The receiver just takes a quick majority vote, sees there are more zeros than ones, and knows the original message was a 0. That's easy. But here's where we hit our first and massive quantum wall. You literally can't do this with a qubit. There's a fundamental law of physics called the no cloning theorem, and it says that you can't create a perfect independent copy of some unknown quantum state. So right off the bat, our simple, elegant majority vote trick is completely off the table. So what now? We get clever. We can't just copy a whole quantum state with all its delicate superposition, but we can entangle it. We can spread this information across 3 physical qubits. So the 0 part of the state becomes 0, 0, 0, and the 1 part becomes 1, 1, 1. It's a neat workaround, but well, this is the huge but. It kind of opens a brand new kind of spooky quantum problem. See, this code is great at catching what we call bit flips. That's when a 0 becomes a 1. It's just like the errors in our classical computers, but the quantum world has this other ghost like error called a phase flip. Look at the right side. It doesn't change any of the zeros or ones. All it does is flip the mathematical sign between the 2 parts of the superposition to our repetition code. That looks like a perfectly fine error-free state. That error is completely totally invisible, and this feels like we're back at square one. Maybe even worse, because a qubit can be nudged in an infinite number of ways. Tiny little rotations, partial phase flips, you name it. How in the world are you supposed to build a system that can fix an infinite number of possible errors? I mean, really think about it. This is a question that had physicists totally stumped for years. If a qubit state can be nudged in any tiny arbitrary amount, well, that's a continuous infinite spectrum of things that can go wrong. You can't possibly build a specific fix for every single one. It seems impossible. And the answer when it finally arrived was just one of the most stunning breakthroughs in the field. You don't. You don't have to fix an infinite number of errors. Turns out you only need to fix 3. Just 3. You've got the bit flip, which we already talked about. You've got a sneaky invisible phase flip, and you've got a third error. That's just both of them happening at the same time. Any weird, arbitrary, complex error a qubit can experience is just some combination of these 3 fundamental types. This is the absolute magic trick of quantum error correction. Think of it like this. An error can start out as any shade of color in an infinite rainbow, but when we design a circuit to measure for an error, we force that error to make a choice. It has to collapse into being either pure red, pure green, or pure blue. So any complex continuous error, when we check for it, snaps into one of 3 basic discrete types: a bit flip, a phase flip, or both. And those we know how to fix. This idea just completely transformed the problem. Instead of chasing this infinite ghost, we just need a solid systematic way to build code that could reliably spot and fix our 3 basic error types. What we needed was a rulebook, and that rulebook is something known as a stabilizer formalism. It works like this. Imagine you've built a perfectly balanced sculpture. The rules of the code are like little checks you can do on the sculpture. If you perform a check and it leaves the sculpture completely untouched, perfectly balanced, then you know everything's okay. But if your check makes it wobble even a little, you know there's an error somewhere. We can actually look at our simple repetition code through this new lens. The rules are pretty simple. One rule checks, hey, are the first two qubits the same? Another rule checks, okay, how about the last two? Are they the same? The only states that can pass both of these checks without causing a wobble are perfect error-free code words 000 and 111. And here's where it gets really cool. When an error does happen, the state fails the checks in a very specific way. Just look at this table. Each type of error creates a unique pattern of pass-fail results. A bit flip on the first qubit gives one result. A flip on the second qubit gives a totally different one. This unique pattern is its fingerprints, or what physicists call an error syndrome. It tells us exactly what went wrong and where it went wrong. And this is the most important part. It does it without ever looking at or destroying the secret quantum information we're trying to protect. So we have a system, we have a rulebook, but the challenges don't just stop there. As we start building bigger and bigger quantum circuits, we have to worry about how errors can spread and combine. This means that we have to graduate from simple codes to building something truly massive and clever quantum fortresses. One of the biggest headaches is that errors love to spread. You can have a single simple error on one qubit, but then you perform a standard two qubit operation, something essential like a CNOT gate, and that gate can take one tiny error and smear it across two qubits. All of a sudden, a small fixable problem has morphed into a bigger correlated mess that your code might not be designed to handle. And just to make things harder, nature throws us another curveball. There are certain safe operations we can do that are mathematically guaranteed not to spread errors. The problem is, a really famous result called the Eastern Kill theorem proves that you can't build a full universal quantum computer using only those safe gates. You're always missing at least one crucial operation. It's a fundamental trade-off. And this leads us to some of the most incredible, state-of-the-art solutions like the Toric Code. It takes a totally different approach. It arranges physical qubits on the surface of a torus, basically a donut. Now the error checks all, simple and local, now only involving a qubit and its immediate neighbors. The real genius is the shape. To create an error that a code can't see, you have to create a chain of physical errors that wraps all the way around the donut either through the hole or around the outside. It's a fortress built not out of stronger walls, but out of pure, clever geometry. And that's really the big takeaway here. The race to build a useful quantum computer isn't just about cramming more and more physical qubits onto a chip. It's about this deeply beautiful and complex challenge of weaving hundreds, maybe even thousands of these fragile physical qubits into a single, robust, nearly perfect logical qubit. The real path to quantum power, it turns out, might be paved less with silicon and more with the incredible ideas from geometry and logic. Thank you for tuning into this episode of Quantlock, and I hope you all have a great day.